Okay, I think we're back. I think we're alive. I think this is for real this time. Um, good, and we're streaming too, so everyone should be happy. Everyone should be happy. Fingers crossed. So let's jump into this exam. This is the 2020 final exam, the written portion, the online portion. You've been doing all year actually as your assignment quizzes. So these are little bits and pieces taken from last year's final. The first question says, fill in the major products, including stereoisomers if applicable, and show stereochemistry for all chiral centers for the following 8 reactions. So the first one is an alkyne, and we are adding 2 equivalents of hydrogen with nickel metal. You recognize this reaction? Yeah. This is from beginning of chapter 8. This is hydrogenation. And we know that if you use one of those 4 metals, nickel, palladium, platinum, or rhodium, you'll add hydrogen twice to bring the alkyne all the way to the alkane. So this one has, if you count the carbons, 2, 3, 4, 5, your product should have 5 carbons as well. And it's just a straight chain alkane like that one. Okay. The next one is an alkene. This is a di-substituted trans alkene, and it's reacting with Br2 in the presence of CH2Cl2, which is a nonpolar solvent. So this is another addition reaction from Unit 8. This one is the one that makes a vicinal dibromide. And we know that the bromine always is going to add trans. So what this is going to make is, because you have a cis, and notice that this one is sort of bent, we would normally probably draw that as a straight zigzag, like that. So what we can do is draw that, and we're going to put a bromine in front, and on the back one, we have a bromine in behind there. Right? Because the addition is always anti. So the 2 bromines will end up on opposite sides of that double bond, which will look like this product we see here. And it turns out for this molecule, it didn't ask you to do this, but if you rotate that bond around, you get this molecule. So if you have a trans alkene and you add Br's trans, you end up getting a molecule that's going to be meso if all the groups are the same on both sides of the double bond. The next one, HCl, this is a reaction from Unit 7. So this is addition, or I guess it's a substitution reaction, where what's going to happen here is HCl is going to protonate the alcohol. The alcohol is secondary, and once you protonate the alcohol to make the oxonium ion, you lose a molecule of water to make a carbocation, and then the chloride from the HCl attacks to give you 2-chlorobutane. Now, when that reaction happens, when you make that carbocation, what happens is you lose your chiral center, you get a flat, planar carbocation, and the chloride can then attack from either side. So what you're going to get is this, and that's going to be 50-50. So what do you call a mixture like that that's 50-50? Yeah, it's racemic. You get equal amounts of both, because this turned out to be an SN1 reaction. If you didn't want to get a racemic mixture and you wanted something pure, you could use a chapter 11 reaction and make like the triflate or the mesylate or the tosylate, and then you could use a chapter 6 SN2 conditions, which would just invert this using NaCl and DMF or something like that, polar aprotic. And then you wouldn't get a carbocation, and then you wouldn't get loss of stereochemistry. So we can use some of the reactions we have in later units to get around that racemic mixture issue. This next one, we have an alkoxide. It's a small alkoxide, sodium methoxide, in methanol, and we have heat. Those conditions should jump out at you right now as an E2. So you want to do an elimination. When you do eliminations now, after chapter 7, we have to consider, is this going to be a Zaitsev rule or a Hoffman rule? In other words, are we going to get the most stable alkene as a product or the least stable alkene, least substituted alkene? And the answer in this case is, because it's a small alkoxide, we're going to follow the Zaitsev rule. You only use the Hoffman rule if you have a bulky alkoxide. And so the most stable alkene that you can get is this one, trans disubstituted alkene. So if you look at the alpha and you look at the beta here and the beta here, the beta, if you go on the other side, is going to give you a monosubstituted alkene, which is less stable. That's what you would get if you used like a terp butoxide, a big bulky base, follows the Hoffman elimination rule. Great. Do we have anybody with us online? 3. You can say hi if you're awake. And look at our battery. It's up at like 12%. Aren't we doing great? Okay, the next one, E, mesyl chloride, pyridine, sodium bromide, DMSO. So this is a two-stepper, and these are using, well, first of all, first reaction is from unit 11. Second reaction is from unit 6. So the first thing that's going to happen after the first step, the mesyl chloride and pyridine is going to give you OMS like that. And then the second step, sodium bromide and DMSO, remember the sodium we dissociate away. So we have bromide, which is a strong nucleophile, in a polar aprotic solvent, which is great for SN2s. And you have a secondary mesylate. And remember, when we see this mesylate, think in our heads iodide. Like, it behaves, it's a very good leaving group like an iodide is. So in our heads, we can kind of like consider it to be iodide, and then we're going to do our SN2. So we're going to knock out that mesylate and replace it with the bromide. And when that happens via SN2, there's going to be an inversion of stereochemistry. So after step 2, the methyl stays the same, and this comes out here and becomes bromide, just like that. The next one, it's again a kind of a two-stepper, although we always write the 2 steps. We never stop it at the halfway point. We have an alkyne, and we're reacting with ozone and CH2Cl2, which is dichloromethane. And then the second step, we add a weak acid, acetic acid here. And what this does, this is oxidative cleavage. This was a end of unit 8 reaction where you split that up the middle like that. And on both sides, you oxidize them up to the carboxylic acids. So on the left side, you get that. On the right side, you get 1, 2, 3 carbons. Something like that. So the only purpose in the second step of that acetic acid is to, well, it's actually funny that acetic acid is added, since acetic acid is one of your 2 products. So that's acetic acid there. But anyway, basically what you do when you're finished this reaction is you acidify it so you get neutral carboxylic acids as opposed to anionic carboxylates. Generally speaking, I think we usually want neutral products when we do these reactions. Next one, G. You have an alkane and you're reacting it with Br2 and heat. So this is a unit 9 reaction where we do radical halogenation. And we said that bromine, when it does radical halogenation, is fairly specific for tertiary CHs, which we sometimes call methynes. If it's a CH, it's a methine. CH2 is a methylene, and CH3 is a methyl. So there is a tertiary carbon on here. And so what this reaction will do is replace that CH with this Hbr. So you just get that. And I only want the organic product. Like the other thing it makes is Hbr, but you don't have to write that in if you don't want. If you do want, you can write it in, but it doesn't matter. The next one, sulfuric acid and water. So someone's like this, you can't just like look at it and see what's going to happen necessarily. It's usually advisable to like write the mechanism out on scrap paper somewhere, because sometimes you'll see things that you may not otherwise see. So for example, this one, the first step that it's going to do is react with H+, and that's going to make this cation here. And that is a secondary carbocation. And remember, when you have secondary carbocations, first thing that should pop into our head is, can this rearrange? And in this case, this one can rearrange. And that can rearrange by taking a hydrogen here and pushing it over there. So this carbocation that we just made will rearrange to that carbocation. Then you get elimination, and this is going to follow the Zaitsev rule. And then the best alkene that you can get is going to be that one that gives you a tetrasubstituted product up here. So let's draw that one in. I feel like this is, I don't know, for some reason I like drawing my alkenes horizontally. So spin it around a little bit there. So this is an example. No, that's not right, is it? I saw sulfuric acid and my mind went to elimination. That's not elimination. This is 50% water and sulfuric acid. This is a mix of water and sulfuric acid. This is a chapter 8 reaction. This is an addition reaction. So what this is going to have then is water attack the carbocation. It'll make an oxonium, it'll lose H+, and our product is going to be this one. So it's usually advisable to check your work, like I just did. You could find some mistakes sometimes. My strategy, by the way, when I used to write tests was to start at the beginning and then just write. If I knew how to answer a question immediately, I'd just do it. And if I didn't know how to do it immediately, or I thought it was going to take a long time, I would skip it and put like a star or something by it and go right to the end. And then I'd add up all the points I was pretty sure I had at that point, which was usually around like 40%. And then I'd go back to the beginning and start again. And it was funny that some questions that like you saw the first time and you have no idea like what I'm supposed to do here, on the second time it was like, oh, that's obvious, you just do this. And I don't know if it's like your subconscious has been working on it and you didn't realize, or something you've seen in a later question triggered a memory or triggered something. I don't know. That's always worked for me. May work for you, may not, who knows. All right, this one's asking us for a complete mechanism. For the following reaction, it gives us starting materials and conditions. And it says, show the stereochemistry and multiple pathways if relevant. Clearly label initiation, propagation, and termination steps. Right there is a giveaway that this is going to be a radical reaction. There are only 2 radical reaction mechanisms that we did. One was radical halogenation, and the other was radical addition of Hbr. That's it from that chapter, I think. The other 2 reactions we did was radical polymerization and radical lipid peroxidation. You don't need to know the mechanisms for either of those. You're not going to be tested on those 2 reactions. So this is radical addition of HBr. We have HBr, we have a peroxide, and we have light. It says hydrogen peroxide. In reality, hydrogen peroxide is not used for this reaction for whatever reason. It's organic peroxides typically, but whatever. We're going to start with our initiation step, and our initiation step is the step that creates radicals from no radicals. And that's going to look like this, where you have your hydrogen peroxide, and I'm explicitly drawing out the oxygen-oxygen bond so that I can break it in two to make two hydroxyl radicals like that. So this is initiation because we started with closed shell molecule, a closed shell molecule, and created radicals out of it. Propagation steps are ones where you start with radicals and end with radicals. So we're going to use the hydroxyl radical we created in the previous step. We are going to react it with HBr, and the arrows look like this, where the HBr bond breaks, one electron goes to the bromine, the other electron gets together with the OH, the hydroxyl radical, and you get H2O and a bromine radical. Starts with a radical, ends with a radical. Consumed a molecule of HBr. Second one is if you take your alkene, I'm going to straighten that bond out. It's just a, sp2. You can flip that around. Only because I don't want it to get too long. And we take our bromine radical. And what we're going to do is we're going to add it to the bond. So one of the electrons in the pi bond moves to get together with the bromine. The other one goes to one of the two carbons that are making up that double bond. And it wants to go to the carbon that's more stable. And so in this case, the carbon that's more stable is the tertiary one, the more substituted one. That will put your Br here, plus your radical on that carbon, unpaired electron. Now, this question asks us to show the stereochemistry. What that means when you see show stereochemistry is use hashed and wedged bonds, or any other way, like if you want to use a cyclohexane chair, that's showing stereochemistry, or if you want to use Newman projections, that's showing stereochemistry too. So let's give that a wedged bond. It turns out that that bromine, when it adds, could have added the other way around too. So let's draw that possibility as well to be complete. You're going to get both, and you're going to get 50-50. So that is a propagation step. There's another propagation step in this mechanism. It looks like this. This gives us our product. Plus Br dot. So obviously the other compound will do the same thing. So what I'm going to, back here. So what I'm going to say here is plus an enantiomer. And that's it. That's the two steps. This is like A, B, A, B, A, B, A, B, A, B. Those repeat again and again and again until you run out of starting material, or until enough termination steps happen that your reaction stops. Termination, you just need one example, show one example termination step. So take any two radicals from above. I'm going to take two BRs, just because it's the least drawing. Starts with radicals, ends with no radicals. So you see, like the way I did this is I kind of drew two products and I said plus an enantiomer at some point. The ways you can do this, like if I ask you something like this and there's two products, probably if you ignored the fact that two products are formed and just gave me one of them, you'd still get, I don't know, 8 out of 10 or something like that. To get full marks, you have to show all of it. But you only have to show the second one really once. I don't want like you to recopy everything the second time for the other enantiomer. I just want you to indicate somehow that you recognize that there's two stereoisomers that form at this step, and therefore there's two products that you're going to get at the end. So I just showed it in the kind of this step right here, that two of them are being formed, and then later on I just, plus an enantiomer, plus an enantiomer, plus an enantiomer. Question B, I guess. Circle the best conditions to carry out the reaction below. You can select PBr3, HBr, or either. So this is kind of going into Unit 11 where we did addition or conversion of alcohols to alkyl halides using HBr or PBr3. And there's some differences, some subtle differences between these ones. So in the first one, you have a secondary alcohol, which is converted to a bromide and undergoes inversion of stereochemistry. If you use HBr for that, what's going to happen is it's going to make a carbocation. That carbocation is going to be planar. You're going to get equal amounts. You're going to get a racemic mix of your two products. Actually, technically not a racemic mixture. Technically, in this example, you're going to get two diastereomers, the cis and the trans, which wouldn't be 50-50 actually, because one of those will be more stable than the other. But anyway, if you want the pure one, you got to go for PBr3. PBr3 will do the inversion. HBr will scramble it, half RNS, because it makes the carbocation. The second one, you notice you started with a chiral molecule, and we ended up with a product that's not chiral and rearranged. That sounds like a carbocation was involved, and that's going to be the case when you use HBr. PBr3 is not going to do that. PBr3 is going to convert to the bromide and invert it. The third one, you have a tertiary alcohol, you have PBr3, you have HBr, or either.
I'm having trouble hearing you. Sorry, could you say that again?
No. Technology with me today, I don't know what it is. This is a pretty subtle one, this last one. It's kind of a fine detail that I probably wouldn't test, but like HBr, it turns out that the PBr3 doesn't work so well on tertiary alcohols. And the reason is that you're asking it to do an SN2 as a second step. SN2s don't work very well on tertiary, so HBr is the better example there. Next question, draw a complete mechanism in major products for the following reaction. Include stereochemistry in intermediates. So we're starting with an alkene, so it's probably going to be a Unit 8 reaction. It's going to be addition, and it's going to be addition of chlorine in a nucleophilic solvent, methanol. And so what we're going to do is start with the addition. We're going to make that cyclic chloronium ion, attack with the nucleophile, and move forward. So it's going to look like this. Cl, Cl. We are going to do something that looks like that, that. 3 sets of arrows in that first step. We're going to add that. You're also going to get the enantiomer of that. So that first chloride could attack on the front or the back. So I drew one stereoisomer, one enantiomer. You can get the other one is going to look like this, actually. In case you're wondering what the second one is. So just be aware that there's 2 different ways this can go. And I'm going to get rid of that plus enantiomer since we decided to draw it. And then you have your methanol, which is going to behave like a nucleophile. And it's going to attack the more substituted carbon. And this is going to attack that carbon too. So what this is going to make on that side is your chlorine is going to be here in front. In that case, it's attacking, you can think kind of from like below. Or if it attacks from the other side, this gets a little tricky. Seeing the stereochemistry sometimes on these ones. It's a lot easier to see if you're on a ring. But what's going to happen is it's going to attack, it's going to cause an inversion of stereochemistry. So if you draw that there, look at me drawing chloride there. It's not chloride. Like that. And then what happens is you have another methanol. We need to remove the H+. And you get that. I just chose one specific way to draw this as well. Like there's lots of correct ways of drawing the configuration of those stereocenters. What should be important is that if you were to look at like that and versus that, if one's R, the other's going to be S. You're going to get opposites from each other. These two molecules are going to be enantiomers from each other. Cool. A lot of drawing there. This is streaming fine, so this will be available online too if you missed anything that's in there. Look at this next one. We were kind of jerks last year, weren't we? Draw a complete mechanism for this thing. These Spiro compounds can be a little bit tricky sometimes. If you look at the lone pairs on the oxygen and HCl, that gives you OH2+, which can then leave to give you that cation. So this is another classic example of a secondary carbocation. If you ever see those Spiro compounds is when you have two rings that are joined at one carbon and you're asked to draw a mechanism. Almost always there's like going to be a rearrangement, and the rearrangement is one of those ring expansion rearrangements. Haven't seen a lot of these, but we've seen a couple. And so what's going on here is this is going to lean over there, and what you're actually going to get just like magic is this thing. So where did that come from? Well, easiest thing to do here is number all your carbons. 1, 2, 3, 4, 5, 6. Over here we still have 1, 2, 3, 4. Our 1,5 bond hasn't broken, but our 1,6 bond has broken. And we made a new bond between 6 and 2, which ends up giving you this shape that you see here. So if it was 4 and 3, it's going to go to 4 and 4. You're going to expand the ring, but you're not adding any carbons here. Same number of carbons as before. This is more stable because you've relieved ring strain and you've made a tertiary carbocation. So for two reasons, this is a very favorable rearrangement. And then we have our chloride left over from step 1, which we can use to attack our carbocation. Like that. So it says show stereochemistry if it's relevant. I mean, there's not really any relevant stereochemistry in here because there's no chiral centers. So we don't have to draw anything out beyond that. I guess technically there is chiral centers. It's not chiral centers, but there's a hydrogen here that could be cis or trans with the Cl hydrogen. I don't know. I'm not getting into that level of granularity. I actually don't know what the major product probably is here. So forget I mentioned it. 3, draw a complete mechanism and show major products for the following reaction. Here we have K terp butoxide. Remember, the first thing we do is we eliminate the K+. So this is a bulky alkoxide. Bulky alkoxides love to do E2, hate to do SN2. They're not good, very good nucleophiles because of all that bulk. And here we have OTS. What's OTS? Unit 11. That's a tosylate. Tosylate. And tosylates are very good leaving groups, so think of them as being like a bromide. And so what we need to do is do an elimination. Will this follow the Hoffman rule or the Zaitsev rule? Yeah, this is going to be a Hoffman rule because you have a bulky. So that means you're going to want to take a hydrogen off of that carbon. So let's draw this thing out. I'm going to draw those 3 hydrogens. Turns out only one of those 3 hydrogens is the one that it's going to go for. Doesn't really super matter for this example, but if you remember when you do E2 eliminations, you always have to have anti-relationship between the leaving group and the beta hydrogen. That was another delightful little fact that we added in Unit 7. So if we take the T-butoxide, this is actually, which one do you think it's going to go for? 1, 2, or 3? 1, yeah. It's going to go for 1 because 1 is coming in front. The OTS is going in back, so they're anti to each other. The other 2 are gauche. Assuming this is, yeah, it is. It's staggered the way I drew it. Okay, take that one, that one, that one. You get Hoffman elimination. And get your alkene there. And that's all I care about. You don't have to draw the terbutanol product or the tosylate that's left over. That's all I need. Draw a complete mechanism. You can see we kind of moved everything that wasn't drawing into the multiple choice section. Draw a complete mechanism and show major products for the following 2-step reaction. This one confused a lot of people. This was like a little minor reaction we looked at in Unit 6, that first step, that people just immediately forgot about. What happens with that is the sodium hydride is a very strong base. It'll deprotonate the alcohol to make an alkoxide. So this was in that, when we first started talking about alkoxides in Unit 6, we said using sodium hydride was one way to make alkoxides from alcohols. Now we have an alkoxide, and we want to react this with CH3Br. I guess they want the mechanism here, don't they? And by they, I mean me. Well, the first one is just, I'm going to make it vertical. H minus. And then we have second step, this is going to do an SN2 like that. No stereochemistry, no multiple pathways. Pretty straightforward in this case. Question 8, fill in the missing reagents, conditions necessary to carry out the following reactions. Be specific, do not show a mechanism. Be sure to delineate 1, 2, etc. if the reaction requires multiple steps. So the first one is just substitution of a bromide with an SH, and there's an inversion of stereochemistry, which suggests SN2 conditions. So let's just use NaSH. And what's a good SN2 solvent? Yeah, aprotic. What's your favorite polar aprotic solvent? You know what mine is, but I want to know what yours is. DMSO, good. When we say be specific, that's what I mean too. Like, give me like a real chemical. Like, don't just say polar aprotic. Give me a polar aprotic. Like, I don't care which one, but just give me one that you would intend to use in this case. Okay, this one looks like an elimination because you're going from an alkyl halide to an alkene. Not only is it elimination, it looks like a Hoffman elimination. So you've got the less stable alkene. So what do we use for a Hoffman elimination? Yeah, bulky alkoxide. ONA. We use the same solvent with it, and we like to use heat for elimination, so it doesn't really matter in this case. You can put it or not put it. I'd be okay with either. Next one is addition of Hbr, but it added anti-Markovnikov. So is that regular addition of Hbr or radical addition of Hbr? You just put Hbr here, which a lot of people did. That's not right. That adds the other way around. That gives you the Markovnikov product. To make it go this way, you need the peroxides. That makes it go the other way around. Lastly, we have the alcohol OH, and we want to replace it with cyanide. So this is one that so many people just put HCN, and I just get visions of poor Gilbert Lewis choking to death in his lab after inhaling HCN. HCN is not a strong acid either, so it's not something you would use in this particular case. This one turns out you need 2 steps. You need to first convert the OH to a leaving group, and then you can convert it into, replace it with cyanide. So the first step, you could just use something like HBr and convert the OH to a bromide, and then in the second step, you could use cyanide, DMSO. You could also, if you wanted in the first step, use like a mesylate or a tosylate or a triflate. It'll do the exact same thing. All right, it's 9:24. I think we should probably stop. All right. Thanks, everybody. And the rest